Welcome again, APChem students. This is Lew Acampora, Science Director for Advanced Kentucky. And today I'd like to review some questions regarding reaction kinetics and integrated rate laws, one of the central topics of the AP Chemistry course and exam. We talked about kinetics, and if you saw the previous video, you would hopefully remember that kinetics deals with how quickly reactions occur, and that in general, there's a rate law. So if we have some hypothetical reaction, A units of A reacting with B units of B to produce some sort of products, then the reaction rate would be defined as the rate of change of the reactants or the rate of formation of the product, so the change in the concentration of A per unit time. And we'd have the expression some constant times the concentration of reactant A to some power times the concentration of reactant B to some other power, where these exponents are not necessarily the coefficients of the balanced equation that reflecting the reaction mechanism. But in general, if we were to graph the concentrations versus time, we would find that starting from our initial reactant concentrations of, let's say, A and B, which are somewhat arbitrary, the concentration of reactants would decrease, and depending on the stoichiometry, let's make this a 2A plus B, then while the concentration of A decreases, the concentration of B would decrease, but not half as quickly. So this might look like that, where I've collapsed this down and started it here. But in general, the reaction rate is going to be fairly complex, a complex curve, because it's going to depend on two things, on the concentrations of both reactants and their orders. And if you have a more complicated chemical reaction with more than two reactants, this could be a very, very intractable term. These curves of concentration versus time, and obviously if we had a product here, and let's make the product 2 units of C, that might start out and do something like this. These curves are algebraically or mathematically difficult to determine. You can do it with a good computer or even a not so good computer nowadays, but they're challenging to get mathematical expressions for. There is a case in which they're much simpler, however, and that's when we have a decomposition reaction. So that's really what the integrated rate law concept of AP chemistry deals with. It's when we have a decomposition reaction, and remember, a decomposition reaction is one in which you have only one reactant, I'll label it R, becoming products. And you could have some coefficient here, it won't matter, so I'll just leave this as 1 for simplicity. In this case, the reaction rate is equal to some constant, the rate constant, times the concentration of our sole reactant to some power. And this power is typically either 0, 1, or 2, and it generates interesting and somewhat mathematically tractable curves. And then we'd call this a 0th order or 1st order or 2nd order reaction. So what would happen in each of these cases? Well, let's think about it, and we'll assume that we start out with, we'll graph this, and have a concentration of our reactant here, and then time will be on the horizontal axis, and we'll start with some initial concentration here, marked there on the curve, and there's my 0 for concentration and my 0 for time. Let's say this is a 0 order reaction. So assume for a minute this is a 0 order reaction. R to the 0 power is 1, and that means that this becomes, reaction rate is just constant times 1. So for a 0th order reaction, and let me color code this a little bit for you. So 0th order, the reaction rate is just K times 1, and I'll just leave out the 1. And that would generate a curve, or not really a curve, in this case I'd generate a straight line where the reactant is consumed at a constant rate regardless of its concentration, a little bit unusual, and that tells us something else is going on, until we get to 0, and then nothing happens, so we have to not be silly about having negative concentrations, but we would see this straight line. And usually this means that this reaction is going to chug along at some rate that does not depend on the concentration of reactant. So in these cases, the reaction rate is determined by the presence of a catalyst or a surface or something else along those lines. But it's fairly easy to understand why that happens, or when that happens, and to see that. And so this would be the differential rate law for a 0th order reaction. More common, or slightly more challenging, is what happens if we have a first order reaction for m equals 1. So this will be a first order, and I hope you can see that in green. This tells us that the reaction rate will be proportional to the concentration of our reactant. So if we start off at this point with an initial reaction rate, a pretty steep slope, by the time we get to half the concentration of reactant, the reaction rate would be half as steep, and that would mean I'd have a line or a curve that had half the slope, and then again I'd have half of this slope, half again, and I would generate a curve that might look like that. And some of you may recognize this as an exponential decay curve, but the important thing for us to know is that where the concentration is relatively high, the reaction rate is high, and as shown by the steepness of the curve, and as the reactant is consumed, the reaction rate slows down and this curve starts to level out. The reactant's always falling, but the curve is always decreasing. We can't be increasing the concentration of reactant for this irreversible reaction, but the rate at which it decreases gets smaller and smaller. And that's a nice calculus problem for some of you who might be in calculus, but we don't need to worry too much about that. In the case of a second order curve, we have the same qualitative effect, but it's really twice as large, in that if the reaction concentration is half, then I have 1/2 squared, and the rate would be 1/4 as large, and that means that I get a graph that comes down more quickly and levels out more dramatically. Never really goes up at the end, so let me try to correct that. But it'll look something like that. And qualitatively, it's very similar to our first order curve. And of course, I'm being very arbitrary here in saying what time is. Some of these reactions would occur in a matter of seconds. Some might require minutes or hours or even longer. But this is a general shape of the concentration of reactant versus time for a 0th, first, and second order reaction. Part of the APChem curriculum is to take these graphs and linearize them. And what that means is generate companion graphs where instead of graphing just the concentration of R versus time, we'll create two other graphs. And I'm going to try to leave this here and make a little room. And the calculus students out there might be able to do this analysis rigorously. But if instead of plotting concentration versus time, if I were to plot the natural log of the concentration of reactant versus time, where now I would get a natural log of the initial concentration here, and typically, because our concentrations are often less than 1 mole per liter or 1 atmosphere for gases, our natural logs might be negative numbers, and that's perfectly okay. You could have a negative log of a concentration. You can't have a negative concentration, but so 0 might be somewhere up here. It doesn't really matter. In this particular case, it turns out that the first order reaction, kinetics, gives us a line. And the slope of this line is negative k, the rate constant. So again, in green, this would be my first order. Zeroth order reaction, which is shown here in red, would come down and then curve downward. So that red is my zeroth order. And a second order reaction, starting from the same point, would come down and curve upward. So that blue would be second. So if I have a first order reaction, I would recognize it because a graph of the natural log of reactant versus time would be a straight line, would be linearized, and the slope of that line would be negative k, where k is the value of the rate constant. Notice in terms of units here, k here would have units of, well, there are no units on the vertical axis because the natural log of concentration is a pure number, so it would have units of nothing over time, or time to the -1 power. It could be seconds or minutes or so forth. The important take-home is that a graph of natural log of reactant concentration versus time is linear for a first-order reaction. And then if I have a second-order reaction, and I'll do that over here, then my axes are going to be 1 over the concentration of my reactant, and those will always be positive numbers. This might be the reciprocal of the initial concentration, and here's time going that way. And in this particular case, a second order reaction is linear, so this will be second order with a slope equal to the rate constant k. Both first and second order, or first and zeroth order reactions would curve upward. So a first order reaction might do this, and a zeroth order reaction, when plotted this way, would curve up even more dramatically. So I can always make graphs of concentration, natural log of concentration, or reciprocal concentration versus time, no matter what order I happen to have, but it's where they're linear that I really care about. The concentration versus time will be linear for a zeroth order reaction with a slope here equal to negative k. And in this particular case, the reaction rate is the same as the rate constant, and it has units of molar per liter, moles per liter per second. When I plot the natural log versus time, a first order reaction gives me a linear plot sloping downward, where the slope here is negative k, with units of reciprocal time. And for a second order decomposition reaction, a plot of the reciprocal of concentration versus time gives me a positive line with a slope that is positive k. These plots generate what are called the integrated rate laws for these reaction mechanisms, which just tell us by an integrated rate law is a plot of the concentration of R versus T in terms of the initial concentration of R and time, and the reaction coefficient, or constant K. So it's some function of these things, of these quantities. For a first order reaction, we can read that off from the curve. The reactant concentration at time t would be equal to the initial concentration minus the amount I've dropped, which would just be k times t. And here is the integrated rate law for a zeroth order reaction. These are going to be given to you in the equation sheet, certainly for the first and second order reactions. But the important thing to notice is that you have 3 different quantities here: a reactant concentration at some time t, the initial reactant concentration, the rate constant, and time. And given any 3 of those, you may be asked to calculate the fourth. And that's a mathematical, somewhat algebraic exercise. For a first order reaction, we could use the linearity of the natural log curve to say that the integrated rate law would mean that the natural log of the reactant concentration at time t equals a natural log of the initial concentration minus KT. And that's one nice way of writing it. Sometimes it's more convenient to take the exponential of both sides of that equation, in which case we get e to the ln of r at time t equals e to the ln of r naught minus kt. This, since exponential and logarithm are reciprocal, is just the concentration of r at some time t. And then I can use my properties of exponentials that the exponential of this difference, or the sum, would be the product of the exponentials. So this becomes concentration of r initial times e to the negative kt. Either of those work for the integrated rate law for the second order reaction. Just depends on whether you like to just have a concentration of r at times t over here. And then just to complete this, for a second order reaction, we'll use a linearity of this curve here to say that 1 over the concentration of r at time t equals 1 over the initial concentration of r plus kt. And I will leave it at that and let those who want to solve for the concentration of r at time t to do so. So those are the integrated rate laws for the zeroth, first, and second order decomposition reactions. These, again, depend on only having one reactant. So it's R goes to products. And that might seem very, very specialized. I mean, how many decomposition reactions are there? And I'm just going to spend a moment here to say that we can, and perhaps you've done this experimentally, but we can generalize this by adjusting our initial concentrations. So I'm going to get rid of these graphs, and you should have a note sheet that goes along with this video production. But let's say we have a reaction that is not a decomposition reaction, but has two reactants. And let me call this reactant A plus 2 units of B going to products. And I'm going to set up a chemical reaction where my initial concentrations might be 0.001 molar in A and 0.1 molar in B. And I don't care about the products. Again, my rate law would be reaction rate is K times the concentration of A to some power times the concentration of reactant B to some other power. Notice under these initial concentrations, I have a very, very large excess of B. So what will happen if this reaction goes to completion is I will use up all of my A, and that means that I will run out of A. It's my limiting reactant. In using up 0.001 moles per liter of A, I will, by stoichiometry, use up 0.002 molars of B, this being a 1-to-2 ratio, which means that I'll be left with a 0.98 molar concentration of B. And this is one illustration that even though B is being consumed, relative to A, these concentrations are rather constant. So this B is acting as a constant. It's changing by 2% over the course of this experiment. So I can rewrite this rate law as K times the concentration of B to some power times the concentration of A to its power. But this quantity here is going to be relatively constant, and I can just call this K prime, some other constant, which means that under the conditions of this reaction, this graph is really, the rate depends only on the concentration of A, so I might call this a pseudo-decomposition reaction in reactant A. In which case, if I needed to know the order with respect to A, well, I would just plot graphs of the concentration of A the natural log of concentration of A, or 1 over the concentration of A versus time, and see where I would get a slope. So I think those are a few notes, not too much I hope, for why the integrated rate law is important and where it comes from. If you have any questions, please feel free to tweet or text me, or preferably email me at AskLewKY, your friends here at Advanced Kentucky. So there are a couple of problems that are on the accompanying handout sheet. One of them comes from last year's APChem exam, which I've modified, and you're given the question, and I'll go ahead and read it to you. At least I'll annotate it, but if you have a chance to pause this video and read the question, this might be a good time to do so. You're given an equation for blue food coloring, which is a very, very complex molecule involving 37 carbon atoms, 34 hydrogen atoms, and a whole bunch of other things. But it reacts with hypochlorite ion, which is present in household bleach. And I'll just write blue 1 instead of the chemical formula, plus OCl minus goes to products. So there's our chemical reaction. Since we are looking at blue food coloring, a very sensible way of measuring or expressing its concentration would be using a spectrophotometer. And in this case, the reaction says that bleach is present in a concentration of 0.1 molar. So the initial concentration of bleach is 0.1 molar, and is a large excess so that the concentration of hypochlorite ion is essentially constant throughout the reaction. The reaction is known to be first order with respect to the hypochlorite ion, so this tells us that we're going to have a pseudo nth order reaction with respect to blue, and then the student generates graphs below, and the graphs, and I'll just kind of sketch them here, are absorbance versus time, and you should be able to predict this, the natural log of absorbance versus time, and then finally 1 over absorbance versus time. And we see dots, and over here we get a nice curve like that. Over here, the dots go, the data gives us a straight line, and over here we get something that looks like that. So what are the questions? And you could probably predict what some of the questions are going to be. Question A says, based on the data given, what is the order of the reaction with respect to the blue food coloring, and justify your response. So before I tell you the answer, you might want to pause the video and write down what you would think. 3, 2, 1, and we're back. Because we get a line here is the most linear on the graph of the natural log of absorbance versus time, that would tell us that the reaction is first order with respect to the blue. So first order would be, I guess, the answer to that one. Part B asks you to write the rate law for the reaction, and you need to be careful to make sure you include everything. You can't just write blue to the first power. The rate law says reaction rate equals some constant times the concentration of blue food coloring number 1 to the first power times the concentration of hypochlorite ion to the first power. You don't need to include the exponents explicitly when they are 1, but you do need to have the rate constant, the equal sign, and certainly both reactants there for full credit. This is a little bit tricky. The next part to graph for the value of this rate constant K. And the trick here is to recognize that even though we're plotting the natural log of absorbance and not concentration here, because Beer's law says the absorbance is equal to the absorptivity of the species, usually the symbol A, times the path length times the concentration, that ln, the natural log of absorbance, would equal the ln of A times B plus the ln of C. So if we were to, and this is going to be a constant for our experiment, so graphing the concentration would just shift this line up or down, but would not change the slope. So the slope of this line would be negative K prime, not quite K, but K prime. There are lots of points here. Using the data from the graph, we have the value down here is about negative 3.7. The value here is negative 0.2. And the time here is 100 seconds, and the time here is 0. So the slope of that line would be negative 0.2 minus negative 3.7 minus negative 0.2 over 100 minus 0, and that works out to be negative 0.035, and the unit there is reciprocal seconds. Since K prime would be the K prime, which we just calculated, would be K times the concentration of OCl minus to the first power, and we know this is 0.1 molar, then K would be equal to K prime over 0.1 molar, and that would give us, with a negative sign there, 0.35 reciprocal molar, reciprocal seconds. And be careful, these are going to be the units. They look a little bit weird, but those are the units for a reaction that is overall second order in both reactants. And then part C goes on to say, in a second experiment, the student prepares solutions of food coloring and bleach with different concentrations. When the solutions are combined, the student observes that the reaction mixture reaches an absorbance near 0 too rapidly. So it gets down here before you can get any data. The student might correct the problem by either increasing the temperature, increasing the concentration of food coloring, or increasing the concentration of bleach. And you're asked to select one of those modifications, which would increase the time for the reaction mixture to reach an absorbance near 0. And this is really kind of, I think, not common sense, but that doesn't have much to do with chemistry. Increasing the temperature causes reactions to go more quickly. Increasing the concentration of bleach would increase the reaction rate without starting from a higher absorbance. But increasing the concentration of blue food coloring, even though you would start from a higher, would increase the reaction rate, but since you'd be starting from a higher absorbance, it would still take longer to get down to near 0. So that would be the answer for that one. And any questions that you might have, feel free to email or tweet to me at AskLew. Okay, we've got two more questions here, and we'll go over them quickly. In question 2, describes another experiment in which a sample of ethanol, which is normally a liquid, would be placed in a previously evacuated, rigid 1-liter container and heated until all the sample is vaporized, and the concentration of ethanol gas is 0.01 molar. A solid copper catalyst is now introduced, causing the following decomposition reaction to occur. So ethanol's chemical formula C2H5OH, and it breaks down into C2H4O plus H2. And these are all gases. And again, predictably, you're given graphs, and those graphs are, I'm going to change colors here, the concentration of ethanol versus time, the natural log of the concentration of ethanol, there's my little abbreviation, versus time, and I hope you guessed it, 1 over the concentration of ethanol versus time. And here we have data points that describe a straight line with a negative slope. Here we have some that curves up like that, and here, oops, sorry, and in order, this is 1 over, and here we have a natural log, so be a little bit careful here that you read the graph more carefully than I did, and we get something that looks like that. So again, you probably know what's coming. The order of the reaction with respect to ethanol and justify your response, And because you've got a line here, a linear graph on concentration versus time, so this is 0th order with respect to ethanol. And because this graph of concentration of ethanol versus time is linear. Part B asks for the value and the units of the rate constant for the reaction under these conditions. And for a 0th order reaction, the differential rate law is simply reaction rate equals K. The constant and the rate of the reaction are the same. So, and we'll have the same units, and those units will be the negative of the slope of this. So K equals negative slope. Again, we will need to pull some data, and we've got data here. This is the point 2,000 seconds at a concentration of 0.002 molar, and our initial point here would be 0 seconds at a concentration of 0.01 molar. So the slope would be delta y over delta x, or 0.002 molar minus 0.0100 molar over 2,000 seconds minus 0 seconds. And if you do the arithmetic on that, I get negative 4 times 10 to the negative 6th. And the unit would be molar per second. And that's the slope, so the value of K would be negative of that. So K equals positive 4 times 10 to the negative 6th molar per second. And that's also the value of the rate constant. The question goes on to ask you to write the expression for the differential rate law and the integrated rate law. So the differential rate law, so it says that the reaction rate equals 4 times 10 to the negative 6th molar per second. That's what we just had down here. It's equal to the rate constant over there. The integrated rate law says the concentration of ethanol at some time t equals the initial concentration, which we have, and you need to be specific here. Don't just put in general formulas. So it would be 0.0100 molar minus 4 times 10 to the negative 6th molar per second times t. And that would be the integrated rate law for this reaction. And then finally, you're asked to calculate the concentration of ethanol in the vessel at t equals 800 seconds, which is right around here. You could extrapolate from the graph, and this would be about 0.00 or 0.01, 0.0068 molar, or certainly easy enough to calculate using the integrated rate law at t equals 800 seconds would be 0.01 molar minus 4 times 10 to the negative 6 molar per second times 800 seconds. And if you do the arithmetic, you again get 0.0068 molar. Important though, to use the integrated rate law to know that it's a zero order reaction and to use the appropriate integrated rate law. And then for a little bit of completeness, we have one more problem, and this is a multiple choice, set of multiple choice questions. And you're given the decomposition reaction of ozone. So O3 goes to 3/2 O2. And don't let those fractional coefficients bother you. That's fine. That's perfectly okay. You're given a data table of time versus the concentration of ozone. And I'm not going to reproduce the data table. I'll just say we start out here at 0, 0.0 minutes, 4 times 10 to the negative third moles per liter. This is in molar, and that's in minutes. And then we end down here at 160 minutes at 0.00065, and then finally we're at 0. So the ozone is completely used up. And we're told that in an experiment to determine the kinetics of this reaction, a sample of ozone with an initial concentration of 4 times 10 to the negative third moles per liter is placed in a 2-liter rigid reaction vessel at a constant temperature of 400 kelvins. The concentration of ozone is monitored over time, and the following data are collected, and you get a whole data table here. Question 1 asks for the concentration of diatomic oxygen when the reaction is completed. Not even a kinetics question, but since every mole of ozone gives us a mole and a half of oxygen, our value would be just 1.5 times the initial concentration of ozone, so it'd be 0.006 moles per liter. As this reaction proceeds, because for sufficiently ideal gases, the ideal gas law says that PV equals nRT, or P equals N over V times RT, and we've got V and R and T are all constant. Number of moles of particles is increasing. Every one of those is giving 1.5 of those. So the pressure will go up because the number of particles increases. And I know many students think of things that don't change, and yes, the mass is conserved, but the number of particles isn't. Now we get to some kinetics questions. You're given graphs, and the exact graphs that you would expect. Graphs of the concentration of ozone versus time, the natural log of the concentration of ozone versus time, and 1 over the concentration of ozone versus time. You're sensing a pattern here. And here you're given your data points, do that, but you're given a regression line. And here your data points, do that, and you're given a regression line. And here your data points, do that, and you're given a regression line. And you're asked for the rate law for the decomposition. Since this is clearly the line that is most linear, that tells us it's second order with respect to, the reaction is second order with respect to ozone. So the reaction rate is K times the concentration of O3 to the second power, second order. And the numerical value and unit for the rate constant, you could determine it from the integrated rate law or from the data, but you're given, if you interpret the data from that graph, you're given a slope here of 8.083 reciprocal molar per minute. So this K is equal to the slope of this line, so K equals 8.083 per molar per minute. And that's a kind of funny unit, but it's one that is right. How would this graph change if we change the conditions? So let me get rid of these graphs since we're not going to use them anymore. And say we have our graph of 1 over the concentration of ozone versus time. Here is the data from our initial experiment. And question 5 asks us, how would this change if we were to have twice the initial concentration of ozone? And remember, this is a reciprocal relationship. So if we double the concentration of ozone, we're going to have a bigger denominator, and we're going to start out lower, but have a line that goes up with the same slope. Excuse me. So we would have a line that starts below our original line, but goes up at the same slope, and that would be choice B. You all had that, I hope. If we were to do yet another trial, another experiment, where we had the same initial concentration of ozone, but this time we performed the reaction at a higher temperature, what would happen? Well, since we're starting at the same concentration of ozone, we'd start at the same point, but higher temperatures increase reaction rates because there's more energy available to break through that activation energy, and we would have a greater slope, and it would curve up like that, and that would be option C. Two more quick questions here, so hang in there. If we now run another experiment, and this time we're going to keep the concentration and the temperature the same, but we're going to add a small amount of atomic chlorine as a catalyst, and the concentration of atomic chlorine might be 1 times 10 to the -8 molar. A very, very small concentration, but atomic chlorine is a very reactive species. We now see where the graphs of concentration versus time, ln of concentration versus time, and 1 over the concentration of time, and these are always the concentrations of ozone, look like this, and like this. So now, because the natural log of ozone versus time is linear, we would draw the conclusion that for the catalyzed reaction, the reaction would be first order in ozone, and you're told it's first order in the catalyst, so the rate law would be option C. Reaction rate would be K times the concentration of atomic chlorine times the concentration of ozone, both of those to the first power. And then finally, you're asked which of these reaction mechanisms would be consistent with this rate law, and since the rate law reflects the stoichiometry of the rate determining step, it'd be pretty clear that the slow step would involve the collision of 1 chlorine atom, not molecule but atom, with 1 ozone molecule, and what might be formed here is an oxygen molecule and an OCl free radical, and then in a subsequent fast step, this OCl would collide with another ozone molecule to give me 2 oxygen molecules and regenerate my catalyst. And so I've got my ozone as a catalyst, sorry, not my ozone, my chlorine as a catalyst, and my OCl radical as an intermediate. And what's left is 2O3 goes to 3O2. Well, thank you. I hope this helps you. You're almost certainly going to see some question like this on the AP Chem exam, but think about what this means. And again, feel free to email or tweet any questions to me. So good night and good luck.